We're interested in experiments with random outcomes, tossing a coin or rolling a dice. And so it's worth stopping and just setting things up carefully so we know what all different quantities we're going to be talking about really are. And so let's start by defining a thing called the sample space. The sample space is the set of all possible outcomes of an experiment. So if it's tossing a coin, it's the set which consists of heads or tails. If we flip two coins, it's pairs. I put brackets around them. Could be two heads, head, tails, tail, heads, tails, and tails. If it's a dice, then it's six-sided, then it's numbers 1 to 6. If it's weather, it could be sunny, rainy, snowy, windy, or whatever. So the important thing to remember, this is a set, so that we understand what the nature of the object is. So we put curly brackets around it to mark it as a set, and it's all the possible outcomes of an experiment. So this has to be complete. So that helps us understand what our experiment is. Now the second thing we're interested in is a random event. So when we run an experiment, we get an outcome, which is an element from the sample space. And then we define a random event. It's something that we're interested in. For example, it could be that a coin comes up heads. Or it could be that if we flip two coins, that the first one's a head and the second one is a tail, or so on, right? So we're defining, we have to specify the event we're interested in to calculate the probability for it. And it needn't be a simple event, it could be a more complicated one. But the point here is that this is also a set, right? It's a subset of the sample space. So it's a set of, the sample space is a set of all possible outcomes, and then for our random event, we define some subset of that which corresponds to the event we're interested in. So for example, the event that it comes up heads rather, is the set that contains heads, and that's a subset of the full sample space, which would have been heads and tails. One head and one tails, that event is either a head and a tail or a tail and a head. Again, it's a set and it's a subset of the all possible outcomes. Die roll less than 3, so that means it's a 1 or a 2. And again, it's a set and it's a subset of the whole set of possible outcomes of the sample space, and so on. So when we talk about a random event, it's going to be a subset of the set of all possible outcomes. So it's worth keeping that clear in your head so that you know what you're talking about, and when you're doing calculations, you know what the quantities you're dealing with really are. Now you'll see sample spaces and random events, both sets, so let's do a bit of revision of sets, right? Just the sets are very straightforward, but let's just go through partly to introduce some notation, partly just to refresh your memory and warm you back up to them. Okay, so here's a Venn diagram that we'll use to draw sets. And when you're thinking about sets, it's really helpful to draw these kind of pictures. So the rectangle here is the sample space. It's the set of all possible outcomes. And then suppose we've got two events. One we'll label E, and that's this square here, and F is that square, and they overlap a little bit. And then, so both of these events, E and F, are subsets of F. That's the notation that says that something's a subset. E and F is a subset of S, and E is a subset of S, which means it's entirely contained inside S. And so there's analogues of addition and subtraction and so on for sets. So here's the first one. This is like set addition. So it's the union. We put a U. It's that a U there is a special symbol for the union of the sets E and F. And what it is like set addition. So we take all the elements of the set E and all the elements of set F, and that's our new set, which is E union F. Now in sets you can't have duplicate entries. So you see here we'll take all the elements from set E and all the elements of set F. There's some overlap, but we just take one element from the overlap. No duplicates. The next one important operation is intersection. It's a little bit like subtraction. So that's got an upside down U is the symbol for it, for intersection. And what we do is we take that's the set of elements which are common to both set E and set F. So it's the elements that are in both sets. And the last fundamental operation is the complement. So it's a bit like a knot or something, a logical knot. We take the so E and we put a C up there to mark the complement. So that's the complement of C. Is all the items which are not in set C. So we have our overarching sample space, which is a set of all possible outcomes. There's our set E. The coloured area in blue is all the possible outcomes which are not in set E. And that's the complement of set E. And so given those three operations, union, intersection, and complement, we can kind of do algebra. We can combine sets and do all sorts of different things. There's a little bit, before proceeding, and we'll look at how we can combine them in different ways, let's just note a few things that are important. One is if we take the union of a set E and a set F, that's just the same as the union of F and E, right? The order doesn't matter. And the same for intersection. E intersection U, F intersection U, the order doesn't matter. And that extends to multiple combinations. We've got three. If we take E union F union G, that's the same as F union G union E. So the ordering doesn't matter whether it's just pairwise or with three or more, and the same for intersections. So ordering doesn't matter. So I'll let you check these ones. So we can do them by drawing pictures, or maybe we'll just draw a picture. So I'll do the first one, and you can do the second one yourselves. So these are De Morgan's laws. We don't need to. We won't be using De Morgan's laws. You don't need to memorize this or anything. It's just to give us practice, right? Just to get us used to using sets and thinking about them again. So suppose we've got our setup where we've got two sets. Let's draw it up here. Let's look at that's our set S. We've got a set E and a set F, right? And I'll just colour them in. So the E union F is the combination, is everything that's in here. So it's all of those guys plus all of those guys, right? That's E union F, all of this stuff. And then if we take the complement of it, that's everything that's outside here. So let me just mark that with hashes. Oops. So it's this hashed area on the outside is the complement of E union F. So that's our left-hand side here. Let's look at the right-hand side. And draw a very rough square. Here's our set E. Here's our set F. Now what's the complement of C? It's going to be, let me change colour here. If I can. Let's make it green, right? Oops. So let's call that F, right? The complement of F is going to be everything out here, right? And the complement of the set E, that blue one, is going to be everything that's not in set E. So that's going to be all, let me draw it horizontally to try and distinguish them. So all of this stuff here, everything that's not inside that circle there. And so the intersection of those So that's the points that are common to both of them. Well, we know, right, so the points inside here weren't common to both of them, right, because they're not in E complement. And the point stuff in here isn't common to both of them because it's not in F complement. So the stuff that's common to both of them is everything that's not inside those two sets, which is everything outside, which is what we had on our left-hand side. So by just drawing these pictures, it's a really good idea. It's what I do myself. When you see expressions like that, you want to check them. You can always check them just by drawing pictures like that. So it's a good practice to do that. Now, when we're constructing random events, we're going to restrict ourselves. So in general, when we're dealing with sets with finite numbers of elements, the restriction doesn't matter. But sometimes, and we'll be doing it much later after the midterm, dealing with continuous random variables, we'll have to deal with sets with infinite numbers of elements. So real numbers, the set of real numbers has an infinite number of elements, right? So it's not that unfamiliar, but because of that, you have to be a bit more careful about how we define events. Now, this is a bit of a digression here. It's just if you're interested. So events, we're going to only construct events by using unions, so this guy here, intersections or complements, by combining those three operations and not any other way. So that means if we have two events, E1 and E2, or if we have a bunch of events, E1 through to En, that EI, right, that I there takes values 1, 2, up to N. So with N events, they're just subsets of the sample space, right? So the intersection of E1 and E2 is a new event. The intersection of E1, E2, and E3 is another event. The union of all of them is another event. The union of all of them is an event. The intersection of them, and so on. These are all, given some events, we can combine them to create new events using these three operations. And there's some consequences of that. That means that the sample space is an event, because if we take any set E, we can always take its complement, which is everything not in E, take the union of them, and that gives us everything. So that's the sample space S. And another consequence is that the empty set is also an event, because if the sample space is an event, then the complement of the sample space is the empty set, right? So this is 0 with a line through it is the empty set. It's not a computer science 0. So it's a set with no elements in it. So the complement of the sample space is a set with no elements in it, because everything is in the sample space. And so that's an event too. And so we're just being a bit careful here, because when things are infinite, we really do have to restrict ourselves to these three operations. When we've got sets with only a finite number of elements, we don't have to be so careful. But it's worth being aware of.